hello everyone. Thank you for coming. Welcome to my presentation. So today I'll talk about the intrusion detection in large-scale IoT systems. So I'll mention the challenges, approaches, and needs. So let's start with a brief introduction. So my name is Othmane Belarbi. I'm a first-year PhD student at Cardiff University, and my research topic is about securing decentralized federated learning-based IDS with efficient local optimization. So let's talk about the environment that we would like to protect. So it's the large-scale IoT systems. So there has been a rapid expansion of IoT systems, and it is thanks to the IoT devices' ability to gather and communicate data, which makes them very powerful. The Cisco research predicted in 2025 and 2030, 38.6 billion and 50 billion IoT devices connected to the internet. And why I'm telling that is because most IoT devices connected to the internet are quite exposed to cyber attacks due to weak security systems. So even better, the same Cisco research group has predicted that as the number of IoT devices connected to the internet cases increases, the number of cyber attacks will increase. So that's why we need a system that will allow us to protect such system. So an intrusion detection system, or IDS for short, is a system that protects a network, infrastructure, or computers for malicious activities or any well-known threat. So it alerts the user or the network administrator whenever there is a potential suspicious activity in the network. So here, in that case, the IDS is placed just after the firewall. So imagine you have an incoming packet coming from the internet. So before the packet arriving to the computer, the IDS will check whether or not this packet is malicious or has any suspicious intent. So traditional IDS base their operation on machine learning models trained centrally in the cloud and then distributed across multiple devices. However, the specific characteristic of large-scale IoT systems brings new challenges that needs to be considered to deploy the IDS in an effective manner. So, for example, in a large-scale IoT system, we have a lot of devices that are highly connected. So they are generating huge amount of data, and most of the time, this data contains sensitive information. So we need to be able to build an IDS that's able to respond in real time by training a model without leaking any sensitive information from the data collected from the sensors. So there are different characteristics. For example, the fact that many IoT devices has limited or processing power or memory or battery. So in that case, the implementation needs to be lightweight and suitable for that kind of device. So there are several ways to deploy that kind of architecture. There is decentralized, the distributed, and decentralized. The centralized architecture is the most common and famous one. It consists in two phases. First, collecting the data from the clients, and then second, showing a chosen machine learning or deep learning algorithm on the cloud side. This kind of deployment is usually done for small network with small scalability, and it can simply explain because if the clients need to transmit their data to a cloud or any third party, this transmission takes time, and if you have, the more clients you have, the more transmission you will have to do. So the bandwidth can be very quickly overwhelmed, and increasing the number of devices will lead to the server being a bottleneck. So it's definitely not suitable for our use case. Then there is the distributed architecture. So this distributed-based IDS is a potential solution in which both the training and inference of the machine learning model is performed locally. So it allows us to preserve the privacy of the data because we'll have one model per client. And however, the main problem is that these models are not sharing any learning experience. So it's limited to a per user experience. And finally comes a federated learning one. So federated learning is a new distributed learning paradigm introduced by Google a few years ago, where multiple clients are used collaboratively to train a model without having any access to the raw data. So it consists in 3 phases. So the first one, the clients will train their local model based on their local data. Then they will transmit no data, but just the model updates the parameters of the model found after training. And then this cloud, this central server, will perform aggregation to create a new global model that is more effective. So the particularity of this method is that since the raw data is not shared, but just the model updates, we are ensuring the data locality and the data privacy. Also, it reduces the network overhead because we don't need to transmit beforehand any raw data with any third party. And it's definitely suitable for a large network with high scalability. So this method has attracted many interests in the application of intrusion detection systems. However, it does come with its challenges. So training in heterogeneous and massive network introduces challenges that needs to be carefully considered and that would affect the performance of the model. So recent studies have shown that actually federated learning is not that private. Even though we are not sharing any raw data, it's still possible to leak some sensitive information from the model updates by performing some inverse operation on the gradients. So federated learning is presenting some challenges that and there is still some work on it. For example, one potential solution for coping with this leakage of information from the model updates will be to encrypt the communication channel, making it impossible for the attackers to infer any sensitive information. And finally, so one work that I would like to work during my PhD would be to work on a new version of federated learning, which consists of removing this central entity. So it would be decentralized federated learning, and hopefully it could solve some issues like the single point of failure, because the central server is the entity orchestrating all the training. So if we remove it, we are able to remove this single point of failure issue and also make applicable federated learning in a peer-to-peer network. So that's for my presentation. Thank you for listening.